And good afternoon, everybody. This is chapter 13 in Anderson's Environmental Economics, and we're getting into the resource management part of the book. And this chapter is called Chapter 13 Renewable Resources. Okay. So let's just go over a little bit about what the chapter is going to be covering. Here we got some populations of Pacific rockfish, and there is certainly estimates that measurable U.S. fish stocks are being overfished. So, what is this chapter going to be covering? It's certainly going to be covering fisheries, but more importantly, it's going to be a model um, of what the appropriate fishing or use of a renewable natural resource is. And keep in mind, a renewable resource is one that can literally recreate itself, unlike, let's say, oil or natural gas that cannot necessarily create itself. And the model that we'll be using for this renewable resource will be that of fisheries. And that model can be used for any renewable resource, whether that would be um, domesticated animals, fishing, um, and and the like. So a fishery is an area where fish are caught, a fishing ground, or a firm in the fishing business. Bycatch is a term used for fish, birds, turtles, and marine mammals caught in a fishery, but discarded because they have little or no commercial value when they do not meet regulatory requirements. Um, The Sustainable Fisheries Act in 1996 stipulates that a species that falls below 25% of the natural population must be rebuilt to 40% of the population. So, as I just said, 43% of measurable U.S. fish stocks are overfished. And there are a number of solutions: closure of the fisheries, quotas, buyouts of fishing rights, and regulation that requires safer fishing equipment. This chapter introduces a popular model of natural resource management using fisheries and forests as the central examples of renewable resources. Okay, so now we go on to something called a biological growth function. And this looks at the relationship of fish stock size and the growth of fish stock per period. And you'll notice that it is an inverted U shape. This is what your book calls a logistic growth function. And we have an initial period of exponential growth, followed by a leveling off as food supplies and other constraints limit further growth. Now, at low population levels, food and space are abundant, but mates are scarce, so low fish stock low correlates to low growth rates. As the population increases, though, there are more mates and higher growth rates until it reaches a maximum. Then beyond that maximum, um, fish population decreases due to space and food constraints. And this is diminishing marginal returns. And what we reach is something called a carrying capacity, where um, the growth rate of the fish population decreases as there's more fish to be more fish that is out there, and eventually we reach this equilibrium called carrying capacity. Okay, let us now go on to one might call this a more realistic function, and this is called a depensated growth function. And this is figure 13.2 in your book. Now, this may be more realistic, and there is a stable equilibrium at each extreme, whereby it is zero or at the carrying capacity. and an unstable equilibrium at the minimum viable population. So let's say we have lower fish populations than minimal viable. There may be so low that it does not encourage growth, and so we would move towards zero. Okay, fish stock smaller than the minimal viable fish population eventually collapses. But when there is more fish, the population will increase in order to reach its actual carrying capacity. All right, so this is a demonstrated growth function. And the minimal viable population is kind of an inflection point, if you would, between moving towards a population of zero and moving towards the carrying capacity. Now we're going to add a catch to this. So now we're adding to figure 13-1, what if we catch fish? All right, so for any given time period, catch equals growth equals stock. The catch can be sustained initially. So let's say we have, as your figure shows here, we have a catch, a certain amount that's being caught, and that is equal to the amount that is equal to the amount of fish that's out there. That's equal to the growth rate. This can be continued indefinitely. However, if the catch is bigger than the growth rate, then the stock size will fall until it equals the actual growth rate. So if we have a catch that is greater than the growth rate, that will the stock size will go down until it equals the growth rate. Okay. And if the catch is greater than the growth rate, then the stock size will rise until it equals the growth rate. So it's a real balancing act between what you catch and the amount of fish that's out there and the growth rate of the fish, which of course is dependent upon mates that exist out there in the ocean or in the lake. Now, the maximum possible catch that is out there is the maximum sustainable yield. So you can catch fish up to this point, and you are able to gain that much fish, but it has to be in relation to the stock that is out there, stock B. You don't want to try to do this with increased stock than stock B. The catch is, no pun intended, or is to determine whether that stock B is the actual stock to equate that sustainable yield, or you're really looking at stock A. Okay, and this finishes our first section.